Welcome back. Section 1.5 is on special types of matrices and partition matrices. We will not work much with partition matrices, but look at special types of matrices. Definitions. A square matrix M by M, matrix Aij is said to be diagonal matrix if Aij is 0 for all I not equal j. What this means is A1 2 is 0, A1 3 is 0, likewise A2 1 is 0, A3 1 is 0. So what is not 0 or could be not 0? A1 1, A2 2, A3 3. I hope you understand. Aij equals 0 for I not j means the off diagonal elements have to be 0. The non-diagonal elements of A are to be 0. The diagonal elements may or may not be 0. So notice the condition is for the non-diagonal elements. The non-diagonal elements have to be 0. So here, non-diagonal elements have to be 0. These are the diagonal elements. They may or may not be 0. So this is an example of a diagonal matrix. Here are diagonal elements. They may or may not be 0. But the off diagonal elements are 0. Here, the diagonal elements may or may not be 0. I don't care. But the off diagonals have to be 0. There are no off diagonals in this matrix, so nothing to worry about. That's the requirement. All the off diagonal, non-diagonal or off diagonal elements must be 0. That's a diagonal matrix. A diagonal matrix is said to be a scalar matrix if all the diagonal entries are equal. Look at that. All the diagonal elements or entries are equal. All the diagonal entries are equal. Well, there is only one entry, diagonal entry, it's equal to itself. These are examples of scalar matrices. A scalar matrix In that's diagonal is called the n by n identity matrix if the diagonal entries are all 1. The non-diagonal entries are 0. Well, it is a scalar matrix. So the non-diagonal will be 0. That's not a surprise. But to be an identity matrix, all the diagonal entries have to be 1. Here is a 3 by 3. That's what I sub 3 stands for. You are looking at a 3 by 3. Diagonal entries 1. Non-diagonal entry 0. This is called an identity matrix 3 by 3. Here is identity matrix 2 by 2. Here is identity matrix 1 by 1. Identity matrix is the multiplicative identity for appropriate size matrices. What does that mean? Let A be an n by n, m and n, m by n matrix and In be n by n matrix. So notice A has m rows and n columns. I has n and n rows and columns. Then how do I multiply it? You see, A has n columns, that's the second index. This has n rows, so I can multiply A to I, where I is on the right. So turns out identity matrix is the multiplicative identity for the appropriate size matrices. So A times In is A. That's what identity means. Here is proof. Let A be m by n matrix, Aij. I be your diagonal matrix, Djk. Why did I use Jk? J is the first index, that's the row index. which is the column index of A. Okay, we do that because I is on the right hand side of A. Now m by n and n by n. Okay, so if I have to multiply these two matrices, notice J becomes the running variable. I and K don't change. J runs from 1 to n being the limit for J. Okay, and the product will be an m by n matrix. Now notice djk, this entry, is 0 whenever j is not k. So whenever j is not k, aij djk is 0. That quantity will be 0 whenever j is not k. On the other hand, whenever j is k, you get dkk, which is 1. So that will be 1 when j is k. J is k. Okay, when j is k, that j also becomes k. So you have aik. Hence A times I is A. Now suppose A is an m by n matrix and I is the identity m by m matrix. So size m. So notice A is m by n, I is m by m. So this time I has to go to the left of A. Okay. So then IMA is A. Same thing, proof. Let I be Dij m by m. So notice Dij. Then A is Aj Ajk, it should be a k here. Ajk m by n. Then Im times A, Dij, it should be Ajk. Mind you, it should be k. I have to fix that typo. Dij Ajk. Okay, j becomes the running variable. Again, Dij is 0 when j is not I. Dii is 1. Okay, same story. J, Dij is 0 when j is not I. And otherwise, it is back to akk. So you get the same Im equals A, the same result. Okay, I'll fix this typo. So that I here should be a k. That I here should be a k. Okay, so we saw that I is a square matrix, but A need not be square matrix. So you needed appropriate size. Well, if A is also a square matrix, then we don't have to worry. A square n by n, I is n by n, so A times I is A, which is I times A. We can check for yourself. This matrix times the identity 3 by 3 is the same matrix back. Place the identity to the left times this matrix, you get that. You will have to check it. Okay, check this multiplication to make sure this behaves like the identity matrix. Identity matrix means it's like 1 in multiplication. When you multiply by identity matrix, you get the same matrix back. Okay. What are powers of a square matrix? Suppose A is a square matrix, say n by n. Let P be a positive integer. Then A to the power P is A multiplied to itself several times, where A appears P times. A has to appear P times. By definition, A to the power 0 is identity matrix, IN. Now A to the power P, A to the power Q is A to the power P plus Q. Why? Because A to the power P, A appears P times. A to the power Q, A appears Q times. So together it appears P plus Q times. What about A to the power P to the power Q? Well, this is exactly like in real numbers. A to the power p appears q times. In other words, A appears pq times. What about multiplication of matrices? Now this you have to be careful. AB to the power p is AB written p times. But note, A and B need not commute. Remember, in matrices, multiplication is not commutative. So I cannot collect all the A's together and all the B's together. I cannot. So this product may not be written in the form of A to the power P, B to the power P. So this need not happen. You may not get this result, because AB need not be equal to BA. So I won't be able to interchange all the A's to push to the left, all the B's to be pushed to the right. So AB power P need not be A power P, B power P. Be very mindful, multiplication of matrices is not commutative. Some more definitions. An n by n matrix A is called upper triangular if Aij is 0 for I greater than j. I represents the index of the row, j represents index of the column. So whenever row number is greater than j number, that is the row index is greater than j column index, this is 0. So how does it look like? Let's see an example there. That's an example of an upper matrix. That's the entry 2, 1. Row index is bigger. This is 3, 1. Row index is bigger than column index. So notice this is 3, 2. Again, row index is greater than column index. In that case, these are 0. So here is an example of an upper triangular matrices. Why you can see why it's called upper triangular. All the non-zero potentially live here. All these lower triangular elements have to be 0. That makes it upper triangular. So what is lower triangular? An n by n matrix Aij is called lower triangular if Aij is 0 whenever the row index is less than j, column index. So here is an element entry 1, 2, 1, 2. That is, the row index is smaller than column index. It has to be 0. This has to be 0. That is 1, 3. Row index is 1, column index is 3. So, and that's 0. So notice how the upper triangular entries are 0. So the matrix is lower triangular. Okay. So I hope there is no confusion. In upper triangular matrices, all the lower triangular elements are 0. In a lower triangular matrix, all the upper triangular entries are 0. Okay? More definitions. A matrix is supposed to be symmetric if A transpose is A. Here is a symmetric matrix. How does it look like? Look at the diagonal and look at the off diagonal entries. They are equal. Okay, so there is a symmetry along the diagonal. That is symmetric. It is defined as transpose of A equals A. Note, a symmetric matrix has to be square matrix because the sizes get flipped. So if they were not square, then you cannot have this equality. What's the meaning of skew symmetric? A matrix with real entries is called skew symmetric if A transpose is negative A. So here it is. Now all the entries are 0. All the non-diagonal entries, all the diagonal entries are 0 and non-diagonal entries, notice the sign, they are opposites. Alright. Skew symmetric and symmetric, they have to be square matrices. We'll continue in our next video.